Let's get rolling. I think we'll just kind of go into it. I was going to do this, but I got a feeling folks are going to still trickle in. Let's just get some stuff. We're here. We freaking made it. Let's do some math. First off, let's talk about what is in the air, what will be coming down pretty shortly here. So there is a web work floating about. There's a web work up. Howdy. Web work. It's like Planar Systems 1. When does that due? Anybody know?
Tomorrow.
Tomorrow. Do we need more time?
Yes.
Yeah.
Cool. I will move that to, let's shoot for Thursday. That seems reasonable. There is a new web work up, and we'll talk about what's on that today. So this one here, this was all complex eigenvalues. I'm trying to organize these a bit. And this one here, we'll actually go back a little bit to distinct real eigenvalues. But these are all about the actual solutions, which I'll put a quick summary up to kind of bring us back up to speed. Distinct real evals. And then today, we are going to cover repeated eigenvalues. So in other words, a single eigenvalue of multiplicity 2. And lambda is the classic. If you see me writing lambda, I'm probably talking about eigenvalues, unless it's modern geometry. Single lambda of multiplicity 2. And this is actually the first two problems in that in this assignment here. So you'll need to do what we did to talk about today. Hello. Someone's calling. Next step is tear it out of the wall so I don't have to hear that. Okay, that's good. I didn't have to rage out, Hulk out. Can't stop doing it. Is there anything you'd all like to talk about? Any questions on the current web work? And also, again, if you have that phase portrait thing, please get that to me today, ideally. Would be great. I realized I had the solutions up, and then I realized after that, oh no, I realized I had them up when I realized at the same time folks were still working on this, so I retracted them briefly. And I think, Katrina, did you have one also?
Yeah, but you go ahead.
So yeah, it's cool. I'm just making sure that that happened. Hi Lou, it's cool.
Oh, I was just gonna ask a question on like the fundamental matrix form of.
Is it the same?
Mm-hmm.
Okay, cool.
Yeah.
Can we take a look at that? Could someone pull that problem up, please? Isn't that nice how that worked out?
Also, I have another question about when the new web work is due.
The new one, oh, that's a good question. This is due Sunday,
Okay.
so like 6 days from now. And I did move this one to Thursday, the current one. That's the one we're going to talk about right now. So I hope I can answer this question, Lou and Katrina. I know what you're talking about. Let's see.
This one.
Yeah, it's just, yeah, so you are, the fundamental, okay, yeah, absolutely. So, this is problem,
It's not touchscreen.
I know, thanks. I'm realizing that. This is problem 1 off this current set. And at some point you will hopefully correctly write C1 times V1. You'll have your eigenvector, you'll have this, C1 is included. You just have to fill in the eigenvector and then e to the lambda that corresponds to that eigenvector. C2 V2 e to the lambda 2t. And you just have to plug in the eigenvectors and some multiple of the some multiple of the eigenvectors and some the correct eigenvalues that correspond to those. And then down here in this, that's part A. In part B, they ask you to fill out the fundamental matrix form for this. So you've got a matrix with 4 slots in it, and then a coefficient vector C1, C2. And this is what we are talking about, right? Just like what, okay, cool. So when I look at what you've done here, I think you just need parentheses around 3t, frankly, but I think that's the issue. So for this one, and maybe Katrina has a different issue and we'll find out, that exponent should have, otherwise you just rate, so if you type this, Lou, you're just, that's e cubed t.
Yeah.
There you go. Oh, and it worked. So for this one, you are just think what matrix rows, when dotted with this vector, give me my solution up here. Now this is going to be composed of 2 different rows. So you're going to have up here, you're going to have C1 times, I'll just kind of do the first row. Let's say I have V11. Let's write the whole damn thing out, otherwise I think we're going to have trouble. E to the lambda 1t plus C2 V21 V22 e to the lambda 2t. So to get here, you need to think about this e function being multiplied inside. So for example, and actually I'll just put it all inside. This is C1 V11 e lambda 1t plus C2 V21 e lambda 2t. And then similarly for the bottom row, but what you need is just these 2 things here to plunk in over here. So this would be V11 e lambda 1t, and then this would be V21 e lambda 2t. Does that help on that, Katrina, or was there a different issue going on? And then similarly down here for the bottom row.
I think that helps. I think I'm gonna have to go back through and like look, because I have a feeling I'm like missing some, either it's gonna be something silly like parentheses, or it's like a negative is in the wrong spot or something.
That's cool. Don't bust your head on it too long. You know, just send me. Okay. I'll take a look at it and see what's up. I can usually debug stuff pretty fast. All right. Yes.
Oh no, I was just scratching my head.
Oh, nice, nice. It was like floating hands. Yeah. Cool. I'm glad you're okay and your itch is scratched. Anything else? Groovy. Okay. So today I want to talk about, actually I want to warm up really quick and make a few pointers about some things. Let's talk about what we know. So quick review, feels like it's been a while. Or summary, whatever. I've got this system, and I wanted to introduce a little bit of new notation today. X dot, Y dot equals this matrix, A11, A12, A21, A22, XY, and maybe I've got some initial condition with this, and I probably do for what we're doing right now. Something like that. So how do we solve this? Step 1, find the it's all about eigenvalues. So let's just do a quick refresher. Let's call this matrix A. And so step 1 is find the eigenvalues of A. From there, honestly, from here, you can pretty much almost sketch the portrait. You just need a little bit of more information, probably the corresponding eigenvectors. So let's just add that in, and corresponding evects. Today we're going to talk about what happens if the 2 eigenvalues are actually the same value. There we will only get one eigenvector, and we have to produce this thing called a generalized eigenvector. So Lou, we actually are doing that. I know we had talked about it a gajillion years back, but we're going to talk about it today. So the eigenvalues, if I have two distinct reals, let's just look at all the possibilities here. So let's say I've got lambda 1 and lambda 2, and just for the sake of it, I'm going to say lambda 1 and lambda 2 are both positive. And in fact, I'm going to say something else. I'm going to say that lambda 1 is bigger than lambda 2. If they're both positive and not the same, this has to be true. One has to be bigger than the other. And I'm going to show you a little tip on sketching this out. So let's say this corresponds to eigenvector v1, this corresponds to eigenvector v2, and there's an art, a craft to doing this. So I sketch the vector, but then turn it into a line. So this is v1, and it corresponds to lambda 1. Let's say this is v2, and it corresponds to lambda 2. So get caught up with me real quick. Sketch those eigendirections. Label them for your brain. I label mine, it just helps. If we're challenged in our creation of diagrams, the more we label, the better life will be. Howdy, boing. So, this eigenvalue here, let's introduce some terminology I can use. The fast eigenvalue is the one with the largest absolute value. And the slow one is the other. That's going to be helpful to us in getting these portraits sketched out. So, the step one, I think everybody's got this. You've done homework on it. We've been doing it pretty much every day. I'm in this case where I've got two distinct reals as my eigenvalues. Lambda 1 is the fast, lambda 2 is the slow. So here's why that's important. Trajectories approach the origin. Right now, the origin is our only fixed point. That will change next week, maybe even Wednesday. Trajectories approach 0 tangentially to the slow eigendirection. That's the one associated with the slow eigenvalue direction. And as they move away from the origin, they become parallel to the fast eigenvalue and become parallel to the fast one eigendirection as we move away from 0. That's super helpful. I use that in my solutions to the thing that if you're going to hand that in, I'll say it for like the third time, if you're going to hand that in, get that to me today, ideally. Move away from the origin. So here, I kind of have to get a few arrows, but let's say I know this. They're both positive, so we're moving away in those eigendirections. The sign of these eigenvalues tells you if you're moving in or out on their corresponding direction. So positive is away, it's growth. Negative is decay, you're headed toward the origin. So since lambda 2 is my slow direction, I'm going to approach it or leave it tangentially. So see, tangentially means like that, or like that, or like that. So when I leave this direction, it's going to be tangentially. As I get further away from it, I become parallel to the other eigendirection. And since we're positive here, we're going to have something that looks like this. And knowing that can absolutely make our lives easy. I don't even have to do a bunch of things here. I can just kind of fill it in from there. Another thing to keep in mind, the eigendirections
are straight line solutions. So there's actually solutions here, and they run right on those lines. They're the only ones that are pure straight lines. So I've got those guys headed out as well. There's my phase portrait. So 0 is unstable. 0 is a source. If you are at equilibrium in this thing, but you get a slight nudge, or there's some imprecision in your computations, and there will be, especially if you're using a computer, if you're doing it exactly, there won't be, you're going to fall off of this thing and careen away from it. So this is an unstable equilibrium. We can also call it a source node, and I probably will slip into both of those from time to time. Look at how nice that is. I didn't even do a damn arrow, right? But I could. If I wanted more precision, I could get a few arrows in here and make sure that I'm syncing up with those as my tangents. Does this sound okay? No? So that's like very helpful stuff. This is true no matter what sign, SIGN, the distinct real values are. So let's look at another case. Let's say I've got lambda 1 is positive and lambda 2 is negative. What do we remember? Anybody remember? What is this going to look like? Just, you should be able to look at that and know what is the fundamental action in the plane. And I'll look away and write some stuff up here. Here's eigenvector 1, here's eigenvector 2. What does this thing look like roughly? You've got flow out on one straight line trajectory, you've got flow in on the other. What do we call that? Semi-stable is really nice. And then what did you say, Katrina? Or did you?
Is it saddle node?
No.
Is it the saddle node?
It's a saddle node. So semi-stable, it's like half stable, half not stable. But especially in the single dimension, we would call it that. But when we move to these planar things, this is a saddle node. We are stable along one direction, unstable along the other. But Cormac, I know you were thinking the right thing there. It was a mix of stabilities. So this thing, let's say V1 looks like this. Again, remember that's actually a trajectory there. And since it's positive, I'm flowing out. And I'm flowing out, and it should actually look like a line, not that weird shit I was drawing. And that corresponds to lambda 1. That's my source direction. I've got a incoming, let's do this one a little more interestingly. So on V2, I've got a negative eigenvalue. So all along that direction, I have a straight line trajectory that's coming in. At this point, I'll just add some trajectories that are consistent with this. Adding a few arrows in couldn't hurt, getting some null clines and things like that. But we're getting a little more sophisticated now. So what happens here is when you're near a trajectory, you act like it. So what I'm going to have is this, and I never can get to 0 unless I'm already there. Because this trajectory takes me in, but this flow takes me away. And then in here, we're going to have little things that look like this. This is all very hyperbolic looking. And I could fill the plane with these beauties like that. And that's just a lot of fun. And that looks pretty bad. So here, the idea of fast and slow isn't really going to apply. But I got a saddle node. Easy. What would this look like? What would this guy look like here if I had had lambda 1 less than lambda 2 less than 0? So let's come back to this. Really the only other possibility. What would change in this?
Sync.
Sync. Yeah, exactly. It's the same portrait. The arrows just go inward. And once you get that, and once you keep this tangential tip and parallel tip in mind, you're going to be a master of sketching phase portraits in the plane. Once we're out of the plane, things become just batshit crazy. And we'll talk a little bit about that, but we won't do it because it's really best for a computer. Any questions on that, friends? That's basically almost all we had. We had one more thing, and that was we had a complex pair. This is what your current web work that you had from last week is on. We have a complex eigenvalue pair. They always come as a pair, alpha plus or minus I beta. And I gotta make sure I get this form right, because I always forget where the negative is on the cosine and stuff. For this one, you're going to don't find the eigenvectors. You don't need that here, because those eigenvectors are complex. And I don't know if you remember what happened on Wednesday, but I took those complex eigenvectors, did a lot of magic, and things became not complex anymore. They turned into sines and cosines thanks to our friend Euler and Euler's amazing identity. We turned these things into something much easier. So for this one, we are going to have our solution. I'm going to introduce a slightly more compact notation. This is actually a vector, solution vector that looks like this. It's x of t, y of t, but compactly like this is c1 e to the alpha t. Whatever the real part is, that just goes in front of t here. And then next to it, I'm going to have cosine of t, negative sine of t, always. Oh, excuse beta t, sorry. I do have the beta in there, so that's beta t as the argument of those trig functions, plus c2 e to the alpha t. And then I'm going to have a sine of t, cosine of beta t, cosine of beta t. Let's talk a little bit about this as soon as you get it written down. This is a C2, my God.
Are those betas the same?
Yes. In theory, perhaps not the way I've written them, but they are the same beta, Lou. They are this number right
or
up here.
Alpha.
And those alphas are the same as well. Yeah, they're both just this real part up here. I'll do a quick example that'll make it clear, hopefully. Notice that the alpha determines whether we have a negative exponent on the e part or a positive exponent or a zero exponent. So if alpha is positive, we have growth that is simultaneously oscillating. We have an unstable spiral. For this, I would say just grab a few, if I asked you to sketch it, can't do that in web work, grab a few vectors in the plane to figure out the orientation. So for this, grab or compute a few direction vectors to determine the orientation. If alpha is 0, I have no e in here. And it's a pure elliptic orbit. Could be purely circular, but it's more likely to be elliptic. So if this alpha is 0, we have what's called a center. And that is just closed elliptic orbits around the origin. Again, figure out what the rotational direction is by just grabbing a vector in the plane and figure it out. What will become important to us is the quality of these. What is the basic behavior here? If we really want the precision of a solution, we've got that right here. We can find C1 and C2 that do our work for us. And then I've got one last case, and that is if alpha is negative, then I have a stable spiral. As t increases in time, This is just e to a larger magnitude negative number. It's headed towards 0. So let's do a quick example. Let's say, let's say I've got a mass spring system. I want to do this again. I want to do this several times. So I'm going back to a thing that's not a system. That isn't a system. But I can turn it into a system and use the things we've talked about to understand what happens. And let's say this. Let's say x at 0 is 4, and x dot at 0 is 1. This is a damped mass spring system. These two outer parts model the restoring force of the spring in relation to gravity. But these are the outer parts that produce these two parts produce the oscillation. This is the term that represents friction. If I didn't have that, then I wouldn't expect decay. But I do have friction here, so this is the friction term. It is proportional to the velocity, x dot. So let's understand this. First off, I can actually crank out a full solution just based upon this. To get, step 1, I have to convert it to a system. I don't expect you to be able to, bless you, do this on your own. I've done it a lot of times. It takes some getting used to. Convert to a system. So we're gonna let velocity equal the variable v. So x dot is v. Our coordinates are going to be x and v. Instead of x and y, we're just going to do x and v. Position and velocity. And we're going to see how those two things relate. So I let that happen. That didn't just naturally occur. This is how you would do the conversion. So if you're like, where'd that come from? We just introduced it. And then v dot, so let's do a little scratch work here. V dot is x dot dot, it's x double dot. It's the second derivative of x with respect to time. It's, what do you call that in physics?
Acceleration.
Acceleration, yeah. It's our acceleration of the system, of the mass in the weights. As the system is moving up and down, it's the acceleration of the mass. Okay, so v dot, I just have to solve here for x double dot. Notice that, take this top thing, x double dot is negative 2x dot minus 2x. I just move that stuff to the other side. I have x double dot as everything else, negated. And this is negative 2v, because I made that substitution, minus 2x. And here I'm going to write this as negative 2x minus 2v. Now I've got my system, and let's write out our initial conditions. X at 0 is 4, and the velocity at 0 is 1. To make sure you're kind of like up on what is happening here, can someone tell us, what did I do to the mass spring system? What happens at time 0? What am I doing? I've got mass hanging on a spring. What does this say about how things start? What are we doing? You look like you're...
Is it that the mass is like 4 units from equilibrium with a velocity of positive 1?
Yeah, that's it. So looking at the math, you're reading the math, right? Mm-hmm. And this is positive extension. Positive, that's extension. That's when x is positive here, x is negative up here, that's compression. So I took the mass spring, it's already hanging at equilibrium. The spring is stretched a little because of the mass. And if I didn't do anything, nothing would happen. If this was 0 and this was 0, our solution is just nothing, just 0 all the time. So I took this thing, pulled it down 4 units. So what we do is we pull it down 4 units. And then, like Lou said, I actually give it a downward velocity. That's a positive number. So I take it, pull it down, and shove it down just a little to give it initial velocity. So it adds a little extra energy to the system. Does that need any extra explanation? Okay, cool. Let's see what happens. So we've got our system. Let's convert to a matrix. So we've got xv dot equals, my matrix is going to be 0, 1, -2, -2. And that's times xv. And then my initial condition, again, well, it's down there. We already got it on the board. Let's find the eigenvalues. Well, I rigged this. So the eigenvalue should be -1 plus or minus I. You could find that by getting the characteristic polynomial, which is lambda squared minus the trace of A lambda plus the determinant of A. That's our formula for the characteristic polynomial. Here I worked that through. It was lambda squared. Here the trace is the sum of the diagonals. It's -2, so plus 2 lambda. Our determinant is +2. The solutions to this are those guys. All right. This, now it's cake because I have this. It just tells me everything I need to know. So our solution is going to be x at t, v of t is c1, and we're going to have, what is alpha here actually? What's alpha? -1, and then beta is what? 1, thank you. So I plug them into this thing I have written on scrap paper. It's e to the -t sine of t negative cosine of t plus c2 e to the -t. Now I've got cos t sine t. If I wanted to now, I could just go ahead and use these initial conditions. Yeah, sorry, what's up, Lou? Did I copy it wrong?
Opposite? Or
It's-
is that?
No, I did do, thank you. Well, actually, in some ways it would work out okay, but you're right, it's not what I had, so thanks, Lou. Thanks for catching that. I was looking at the wrong part of the board in the glare, and sure, I'll use that as my excuse. So I've got cos negative and then sine cos. Thank you. Thanks for keeping me honest here. So to find the C1 and C2, go to the initial condition. At t equals 0, x equals 4, v equals 1. So this means I have 4, 1 equals C1, e to the 0 is 1, cosine of 0 is 1, sine of 0 is 0. Plus C2, sine of 0 is, same thing here, that's just 1 at t equals 0, and then I've got 0, 1. So you could just like kind of pluck this right off. C1 is 4 and C2 is 1. That's what'll make this work. And so my final solution is I plug these back into that beast and I'm good to go. So it's 4 of these, 1 of these. Not bad. You have to do this, I think, on the homework, the web work. Pretty sure you have to do this on the web work. That's how you do it. But if I was going to do a qualitative, so that is a quantitative analysis, that is precise. What if I just want to understand all solutions at a glance? Then I make a phase portrait. So the qualitative solution is, I've got my eigenvalues. -1 plus or minus I, what kind of, what do I expect in the phase plane? What do my trajectories look like? Yeah, it's definitely got some orbiting. When you see an imaginary, you've got spinning in some direction. What else do I have? What does this do?
Negative, so it makes it a kind of a sinky situation.
It's a sinky situation. It's a drain. It's a stable spiral. So this says rotation. This says stability. So I have stable spiral. So I come down to the plane. I know it's going to either go it's going to go clockwise or counterclockwise. Here's where I grab a vector. So let's just grab an easy vector and figure out where how the flow is going. To determine direction of rotation, and I'm going to plug it right into the system here. Let's see, here's x and here's v. Let x equal 1, let v equal 0. So that's going to make, in the system, x dot is 0. There is no horizontal component. This is great. I'm going to be moving up or down. What am I going to be doing? I'm going to be moving down because v dot is -2 when I plug this into there. So this is this guy, right? At 1, 0, I've got a downward arrow. Now I know what's happening and I'm just going to wing it. I don't know exactly the shape here, if it's elongated, but it doesn't really matter. This is what's happening. I never get to 0. I just get closer and closer to 0. Think about these e's that are here, they will never equal 0. They just get smaller magnitude-wise. So here's my solution. What does this say? Well, it says that initially, and actually we could even get our precise one out here, right? Our exact one was 4, 1. So at 4, 1, let's just say that's this. Why not? It could be anywhere. Let's put it there. What happens? Well, since I shoved it down, the position still keeps increasing a little bit. It keeps pushing down because I shoved the thing down. So it's going to go down a little bit. So this is max extension right here. And then the spring force is going to equal the force of the force of the mass moving down, and it's going to, at that point, turn around, and the spring's going to start to win. So it's pulling me back. So x, my extension decreases. This is the equilibrium right here. So at x equals 0, this is the midline. This is equilibrium. And I'm actually at my maximum velocity right there. That's the greatest velocity for the whole system ever, because things just decay from here on out. And then this is max compression right here. X is negative. And then again, I'm here and I'm back to max velocity. This should probably be tangent like that, but or there should be a horizontal tangent there, but it doesn't really matter. And then this is, again, max velocity. Well, it's not max velocity. Let's just leave these three things labeled. It's as fast as it'll ever go again at that point. So the sketch of x versus t is going to be this. I have 4 extension. I've got a velocity of 1, so I've got a tangent slope of 1 right here. So m equals 1 right at that moment. And we come up, we come down. And then as the energy in the system dissipates because of friction, we do that. And hopefully you can kind of see these two giving me the same information in very different ways.
No, you're scratching. It's all good, sorry. I'm gonna make you paranoid. Any questions on that? That's it for that.
So the test, are both of these acceptable?
Have you, what?
Or both of the, like,
Yeah, no, I'll let you know. What do you think about tests already? I know, man. Don't ask that. I'll let you know. You know me. You know. And if I didn't tell you and it was ambiguous, I'll hook you up. Let's talk about the last situation, repeated eigenvalue. And then we have everything covered on Wednesday. I'm going to show you a holistic way to put all these together.
And then at some point, we will talk about bifurcations in this craziness. We will have bifurcations in the plane. And it's pretty wild. So, very excited about that. But we got a little bit more to go, not much more to go. All right, so repeated eigenvalue. Let's say I've got something like this, and my equation, characteristic polynomial looks like this. Can be factored into this, so you've got just lambda naught as your only solution, but it has multiplicity too. So in this case, we've got two main situations. Here's the chill situation. So two situations. My A matrix, the matrix that defines the system, the coefficient matrix, looks like this. It's got lambda naught here, and zeros in the pockets. So that would look like this. E.g., I've got x dot equals, I'm just making sure I'm saying this right, yeah. X dot equals lambda naught x, and y dot equals lambda naught y. That's what your system would look like. It's decoupled. The two equations don't even know about each other. This is like the oblivious relationship or the narcissist relationship. Two narcissists colliding. What will happen? Who can say?
So they aren't parallel.
When you say parallel, what do you mean?
Like if I think about like, oh, they don't know about each other, so like they don't have like a common solution.
They do have a common solution. When x is 0 and y is 0, then both things are true. So don't think, you're thinking in terms of linear equations that are static, Lou.
Okay.
You're thinking in terms of like, just like I've got two equations and just two regular variables. Here we're gonna have actually infinitely many solutions, because that x and y are moving critters. Those are functions. So it's a little more complicated than that. Does that kind of sound good? So when I have this, every direction is an eigendirection. Every direction. You can prove this to yourself. This is just a multiple of the identity matrix. So it sends every vector to a multiple of itself. Every direction is an eigendirection. That's crazy, but it makes our lives really easy. So here, all we have are straight line trajectories, because everything's an eigendirection, and that is the solution. So we get straight line trajectories all through the plane, all headed to 0, the origin. So they're going to look like this. If lambda is negative, If our eigenvalue is negative, we have stable. These are called stars. So this would be a stable star when lambda naught is negative, and then I could have an unstable star. That's sweetness. Unstable star. That's easy. Life is great then. You can easily compute every trajectory. In fact, every trajectory will look like this. Let's see if I had a precise solution. If x at 0 and y at 0 is x naught, y naught, then I'll be at a point like that. Let's say x naught, y naught. I just head straight in. So it's literally just multiples of that vector right there. Our solutions are x of t, y of t equals some constant c e to the lambda naught t x naught y naught. I'm not sure if that multiple is even needed. Maybe not. Guess it depends on what we picked here for x naught y naught, so let's leave it. So that's the easy case. Here's the not easy case. Your matrix either looks like that and has lambda naught twice, or it doesn't look like that and it has lambda naught twice. So what will that look like? So case 2 is A is got lambda naught, bless you, lambda naught, and then there's something non-zero in the pocket, A pocket. And then you've got a 0 in the other pocket. That's probably what it's going to look like. In this case, what do we got? Well, step 1 is find the eigenvector. So find the eval, that's easy. Here's a little tip. In a diagonal matrix with a 0 in one of this pocket or that pocket, the eigenvalues are on the diagonal. If there is a 0 in the lower left, don't confuse this, it's easy to confuse. It has to be the lower left or upper right. Corner, eigenvalues are on the diagonal. So I can just look there and go, oh, lambda naught is my eigenvalue, and it's my only one. It's got to be that way. And then I see a non-zero thing in the pocket and realize I got trouble, so I got to do more work. So find the eval. Here, that's lambda naught. Just read it off the diagonal. Step 2 is find the eigenvector. So find the corresponding E vector. Let's say that's V1. Same way you would normally do it, except it's going to be a lot easier. Because you're going to subtract lambda naught from there. A little note here, it could also look like this. Lambda naught 0, non-zero. The non-zero could be in this pocket. One of those two. Jesus Christ. Hey, buddy. All right, so find the corresponding eigenvector V1. This gives us one solution. So this gives us a straight line solution that we can just call upon. We got a solution. x1 of t is c1 e to the lambda naught t v1. Done. That. That's a solution. It's cruising in or out on the eigendirection. Here's where things get interesting. We would like a second solution because we have the plane and stuff, right? So if I leave my solution at that, I can never incorporate an initial value that's off that eigendirection. So if this is V1, let's say it's corresponding to lambda naught. If I pick a point out here, what am I going to do? If I pick a point here, I can hit it. But this line, if I'm just given vectors in this line to describe everything, I can't do things off the line. So we've got to come up with another vector, and that's the idea of a generalized eigenvector. You probably didn't cover this in linear algebra here. Is that true? Who had linear algebra here? Did you cover generalized eigenvectors?
I don't remember.
Did you cover eigenvectors?
Yes.
Go. Okay, good. So the generalized ones are usually a much more advanced topic, but don't sweat that. Even if you haven't had linear algebra, I got you covered. This is a pretty straightforward process. All right, so step 3. I hate this pen today. Find a second vector. Second generalized eigenvector direction. So find a second direction. Probably should put that up here, English-wise. A generalized eigenvector. Easy process. Step 1, I'll outline it for you. Part A, choose any W not on the eigendirection you already know about. Not on your known eigendirection. We'll do this together. Let's just get the plan laid out. So again, this picture that I just erased, this pen that I'm hating so bad. Oh, here's a whole bunch. I bet these are sweet. I bet these are really nice. Yeah, nice. Good. Oh gosh, I'm sorry we suffered so. So this is my first vector that I already know about. I found that beast over there. I'm gonna pick some W that's not on there. Just as long as it's not a multiple of it, you're good to go. So choose any such W. Then compute, I'm gonna write this up, A minus lambda naught I, I'm gonna write what I mean, W. What does that mean? Well, this is the original matrix, coefficient matrix with lambda naught subtracted from the diagonals. It's literally the one you use to find the eigendirection over there. So once you create your matrix where you subtract the lambda naught off the diagonals, just keep that. Keep it around because you're going to use it right again with lambda naught subtracted off the diagonals. Off the diagonal. And this is going to equal some multiple of the original vector, V1. So it will equal a multiple of the original vector. But it'll be potentially a different multiple, probably. V2, once you find that, what we're actually interested in is that alpha. So then let V2 equal 1 over that alpha times V1. I know this is weird ass. I can't go into the theory of why we're doing this because we don't have enough time. It would take like a week of just building shit up. You can read, I'll put some stuff up so you can learn about why this would be what we do. Otherwise, just trust me. it's gonna work out. Let V2 be this. Then X2, our second solution, is going to equal C2, some arbitrary constant, times e to the lambda naught t V2, this guy, plus t, the variable t, so that's a new variable, times V1. There we go. And our general solution is just the sum of these two critters. We're done. So that's straightforward but weird. Let's do one. And this is how you will do the first two problems on the new WebWork. So, example. All right, x dot equals, let's do something kind of interesting. 5x and y dot equals x plus 5y. Make that 3x plus 5y. And then let's say x at 0, y at 0 equals, make sure I don't pick a direction, 1, 1, just make life easy. Okay, so step 1. Can you do me a favor? I have to pee really bad. So could you please do steps 1 and 2? Could you find, actually just start working on it. I'll be right back, just start cranking and I'll be back momentarily. feeling okay, sanity check up there. Lambda, our eigenvalue is 5. This is like low-hanging fruit. Eigenvector, good on that. If you get to pick something free, pick 1. And not 0, otherwise it's kind of boring. And not an eigenvector. All right, so that is V1. And then pick anybody who's not on the y-axis. There's a cool guy right there. Doesn't have to be that. You're okay, no matter what you pick, as long as it's not on the y-axis. No, duh, yikes. That was scary. I don't want to have to retract everything I've said. Key things to check out to figure out what multiple that was of your original eigenvector. For me, it was 3. Probably this should be the same for everybody, I think. What's up, Lil? Yes.
So when you, like, lambda naught,
Here.
that's 5, right? So, like,
Yes.
How are you
Yeah.
translating that?
I'm subtracting that off the diagonal. So I subtract this, just says take that eigenvalue, which I think we agree is 5, right?
Yeah.
Subtract that off the diagonal, and I get
Before you multiply it by
Yes. the W. Yeah, yes.
then the I doesn't matter.
This is just the identity. This isn't that I. This
Yeah.
is the identity matrix 1, 0, 0, 1. So just think of this as subtract lambda naught off that diagonal. Does that make sense? Does that clear up what was issuing in your world? Yeah? Okay. So here I get alpha is 3. And I can pretty much just write out my whole solution now at this point, using the rhythms that we have. So x2, our v2, is 1/3 times the original v1. That's going to be, what's my v1? It was 0, so it's 0, 1/3. It's weird because it looks so much like the original, but it's got a very specific property that I'll send you some stuff to understand. So my x2 t is going to be c2e to the 5t times 0, 1/3 plus t times 0, 1. Lou, questions?
I was just looking at the initial condition for
Oh,
that x, and it, I don't know how.
did
you
I
got-
pick?
I don't know how
pick
you can
poorly?
get. I don't know how you can get.
Oh,
one with
actually,
what
I
you gave
picked
us.
really dumb. No, I didn't. I don't think I picked dumb one. Yeah, let's take a look in a minute
Okay.
and see.
Yeah,
Yeah, I see what you mean.
Yeah, I was just getting 0 out. That was
Uh-huh.
all. And
Yeah,
like
no,
it's just held at constantly at 0.
You've got me scared. Cause yeah, when I look at that, I see how we're not gonna hit that, cause it's actually not linearly independent multiple. I'm pretty sure, that's kind of like a nightmare scenario, but I'm pretty sure. Let me just look at my notes, make sure that I've told my story properly. Did I do V2 plus 2V1? Yeah. yeah, actually, this is very much just like the example that I already had. But how the hell do we hit that? How do we hit that eigenvalue? Or that initial condition? Because this thing here is just a multiple of the y-axis. This is on the y-axis, right? This guy is on the y-axis.
Does it have anything to do with, inverses? Like that 1/3, you take the inverse, it would be the same as the.
I see what I did wrong. sorry, Lou, I didn't mean to interrupt you there. Yeah, at all. I think that it actually should be, V2 should be, this should be W. That's the problem. Got it, sorry. Woo! Go back and check that out. That should be W, which is not on the damn line. Yes, my notes are actually incorrect. So let's just say, yeah, it's exactly that, Lou. Sounds good. Sounds hella good. So it's an easy tweak. That should be W, and then this should be, oh, that's okay. Everything else is okay. This is just the only correction in there. I'll add that to the video notes. And that means that V2 is 1/3 0. Yay, okay, good shit. And this should be 1/3. And this should be W here. And this should be 1/3 0.
What? Oh wait, never mind.
Oh please tell me there's not more.
There's nothing.
Okay. But thank you for your furrowed brows. I deeply appreciate. So our final solution is this. I want to show you how to do the qualitative version of this, which is pretty chill. It's going to be C1 e to the 5t, and then what was x? Do I have it up here? 0. Thank you. What was it?
0, 1.
Thank you. Plus C2 times that critter, e to the 5t, 1/3 0 plus, and you could put these all together. That'd be 1/3 on top, and then in the bottom just t. So that's kind of nice. That actually makes that a little cleaner than carrying around all those pluses and stuff. And so now I can actually hit some things, which is good news. So the fact that x at 0 is 1, 1 means when I plug in 1 here, when I plug in 0 here, we're going to get C1 times 1 times 0 plus C2 times 1 times 1/3, so 1/3 C2. And then I think in the bottom, I'm going to get C1 times 1 times 1 plus C2 times 1 times t, but t is 0 here, so I just get that. And that tells me that C2 is 3, C1 is 1. And I can plug those back in and get my solution. I'm not going to rewrite this shit. We can plug those in and we're good to go. Terrifying. Sometimes it is a tightrope walk up here. And then you start to like, I'm losing it. Is there any questions on that process? Yes, Courtney.
If you were to have 0 in like the upper right or lower left there, would there ever be a case where the other diagonal wouldn't be the same number?
Can you give me a matrix like what you're thinking about?
Like
All
5,
right.
0, 3, 4.
Oh, so in this case, these are two distinct eigenvalues, and it's that first case we covered.
Oh, okay.
So here, yeah, lambda is 5 and 4.
Gotcha.
Cool. Good question. Yeah. All right. How do I sketch the phase portrait? This is the exact solution The face portrait is super chill. It's somewhere between a spiral and a stable node. It's a weird thing. We call it a degenerate node. And anytime we can use this, use the phrase degenerate math, I'm in. Count me in. Phase portrait is a degenerate node. You lousy, you degenerate. How do we sketch you? So we got X and Y. It's kind of the same plan, except we only have one eigendirection to worry about and one eigenvalue. This generalized eigenvector will not come into play as we sketch the portrait. So all you need to do is take the original eigenvector, sketch it, flesh it out into a line, forget about the generalized one. If you are stable, let's say here that we're stable. So here, the lambda naught is negative because I'm moving in. What you get is exactly like what you get in the second phase portrait that you just got back from me, or you're turning into me, or you're avoiding talking to me about. It's one of those. It's that second phase portrait is one of these. If you go through and you crank that thing out, I forget what the eigenvalue was, but it's repeated, and you get something like this. The same thing still applies as you approach. You've got the both worlds happening in this one because this is both your fast and slow. So you approach tangentially and then you become parallel as you move out. And so over here, same kind of thing. I'm going to approach tangentially and then become parallel to the same vector as I move out. And then you just flesh the plane out with these things. You see what I mean? Like a half spiral kind of thing going on there. On Wednesday, we're going to look at a holistic way to see everything that's happened over the last 3 days in one picture. And it's magnificent. And it kind of helps us get ready for bifurcation study in these systems, which will be purely qualitative and extraordinary. So that's all I got for you today, friends. Thank you for showing up. I appreciate it. It took all my strength to get here. I had to cancel office hours, as you know, to clean my car off. Because when you're old, it takes an hour and a half to think about cleaning your car off. If I did not get one of these phase portraits from you, ooh, look, there's a nice degenerate spiral. This is Trayson's. This is Trayson. See, Trayson's got a nice degenerate red thing in the bottom there. Oh, Katrina, I do have yours. And Tara, I've got yours too.